Welcome to our video. We're group number 7 from section 1, which group members are Catalina Pedraza, Angélica Villamil, and Isabella Rojas. And today we'll be presenting our first lab practice called Molecular Dynamics. The presentation of this practice will be shown in the following sections, which are introduction, methodology, results and discussion, and finally we will present our conclusions. But what is molecular dynamics? Well, this is a computational simulation method that allows the analysis of molecular interactions at an atomic level over time. Various physical chemical properties can be determined using molecular dynamics, such as viscosity, solubility, and phase changing temperatures. One of the most important tools for molecular dynamics is called GROMACS, which is the tool that was used for this practice. This tool is often applied to large biomolecules such as proteins and nucleic acids, but it can be used for other types of molecules too. Um, Using molecular dynamics has helped challenging processes of designing and optimizing new drug candidates to accelerate, which shows that it has a very important place in the industry. The fluid that will be analyzed in this practice is water, which in its liquid state has different intermolecular forces, such as the van der Waals forces and Coulomb forces. And what will be measured in this practice is viscosity, which is the friction between molecules passing each other in the fluid. And the larger the intermolecular forces are, the higher the viscosity is. Other factors that affect viscosity are temperature and the shape of the molecule. So, having into consideration the information set into the introduction, our objective here was to use molecular dynamics in GROMACS to evaluate the effect of temperature on water viscosity. Now we will present the methodology used for this practice. For molecular dynamics, several steps need to be followed, which are minimization, heating the system, equilibration, and production. After setting up the file with our mathematical model, which in our case was TIP3P, the minimization step can begin, where the potential energy is minimized due to this relation between force and energy, which shows that if the energy is too big, the force could be too big too, and the simulation could fail. After this step, the step of heating the system starts, where kinetic energy is added to the system, so the temperature increases. After this, the molecules are allowed to move freely, and the kinetic energy is moves around the system evenly. This is called the equilibration step. And finally, we have the most important step called production, where the trajectory is obtained and where we have kinetic energy, potential energy, energy related to polar and nonpolar interactions, and total energy, and the temperature. In this case, we're using a box of 4 nanometers at three different temperatures, which are 303, 333, and 363 Kelvin. And thanks to the molecular dynamics, we can calculate the kinetic energy, the potential energy, the energy related to the polar and nonpolar interactions. We can also obtain information about the viscosity, the temperature, and obtain the trajectory. Thanks to these results, we can create graphs in MATLAB and analyze them. And this must be done for every temperature and repeat this process of simulation for all three temperatures. And then this can be compared and analyzed.
Now we are going to present the results obtained after performing the simulation. First, we have our results regarding the potential energy minimization stage. To eliminate any unusual collisions or geometry that will artificially increase the energy of the system, we need to relax this structure by running an energy minimization algorithm. We can see that for the three simulations at different temperatures, the same graphs were obtained. Here we have an exponential decrease of the potential energy to minus 9.2885 times 10 to the power of 5 kilojoules per mole. This is due to the fact that, as this is the first step of the simulation, the temperature of the system is not yet considered. Now we are going to see the results of our heating stage. In terms of temperature, we can see that when the system was heated for 100 picoseconds, an increase in the temperature as a function of time was obtained. Comparing the three systems, we notice that at higher temperatures we have a greater slope. For the first system, we can see that the last recorded value was 303.85 Kelvin. For the second system, it was 334.7049 Kelvin, and for the third system, it was 362.1519 Kelvin. Now, talking about the kinetic energy in the heating stage, we can see that as the temperature increases, the kinetic energy also increases, and a more pronounced slope is presented. In this case, the first system ended up with a kinetic energy of 1.3 times 10 to the power of 5 kilojoules per mole, the second with 1.4 times 10 to the power of 5 kilojoules per mole, and the third with 1.6 times 10 to the power of 5 kilojoules per mole. The last variation that is reported in the heating stage is the one of the potential energy. As we can see, as the temperature increases, the potential energy decreases, and this is more evident when we compare the final value of the potential energy in each system. For the first one, it is minus 7.0974 times 10 to the power of 5 kilojoules per mole. For the second one, minus 6.8516 times 10 to the power of 5 kilojoules per mole. And for the third one, minus 6.6347 times 10 to the power of 5 kilojoules per mole. Now we move on to our equilibration stage. During the time that the equilibrium stage lasts, temperature fluctuations can be seen for each simulation. This is because in this stage, all the parameters must stabilize in order to run the simulation correctly. However, when we take the average of the temperature for each system, we can evidence that the difference is not significant. In terms of kinetic energy, we can see that there are also evident fluctuations as with temperature. These fluctuations are around the initial energy values established for each simulation, being the average energy for the first system 1.3451 times 10 to the power of 5 kilojoules per mole, for the second 1.4775 times 10 to the power of 5 kilojoules per mole, and for the third 1.6115 times 10 to the power of 5 kilojoules per mole, pretty similar to the values obtained at the end of the heating stage. Finally, for the potential energy, fluctuations also appear around the initial values for each simulation, being the average energy for the first system minus 7.0880 times 10 to the power of 5 kilojoules per mole. For the second, minus 6.7994 times 10 to the power of 5 kilojoules per mole, and for the third one, minus 6.5167 times 10 to the power of 5 kilojoules per mole. It is important to notice that the behavior of potential energy regarding temperature remains.
Now we move on into our production stage. In terms of temperature, it is possible to see how the molecules start to move freely and a trajectory is obtained. In the graphs regarding the change of temperature through time, it is possible to see a swinging behavior within the data and how the values start to fluctuate between a certain range in temperature. At 363 Kelvin, the values fluctuate between 358 and 368 Kelvin. This means that the temperature increased and the molecules gained more energy and are moving freely now. In regards of the kinetic energy, the graph also shows a fluctuating behavior. It is possible to see that when the temperature is increased, the value of kinetic energy also increases. This is because the molecules are receiving thermic energy and in result their movement becomes faster. This way the kinetic energy increases. It is possible to observe this pattern through the three graphs because the highest temperature has the highest kinetic energy average. Then, the potential energy is presented in regards of time at different temperatures. The behavior of the graph is also fluctuating between negative numbers. The potential energy decreases when the temperature increases because this energy is related to the Coulomb and van der Waals intermolecular forces. When the temperature increases, there is also an increase in the kinetic energy. This will create more movement within the molecules and in result will create more distance between them. As we know, the Coulomb and van der Waals interactions get weakened when the distance gets bigger, so in consequence, the potential energy ends up decreasing. The total energy is the sum of the kinetic and potential energy. It is seen through the graph how it has an oscillating behavior and it increases while the temperature increases too. The temperature of 363 Kelvin has the biggest total energy, which means that there will be more movement in the molecules. In terms of the molecular interactions, we are in the presence of Coulomb and van der Waals interactions. The Coulomb interactions describe the electric force in which two charges interact. In this case, in water, this force has an oscillating behavior, and because of the nature of their opposite charges, this force is negative. In this case, it is seen that by increasing the temperature, the force will decrease and the molecular interaction will be weakened. In terms of the highest temperature, we are able to see that in 363 Kelvin, the force decreases in comparison to the average force generated in a temperature of 303 Kelvin. Next, we can see the behavior of the van der Waals interactions. These are interactions between polar molecules, in this case, water. It is possible to see that the force has an oscillating behavior, and while the temperature increases, the average value related to the force will decrease. Because the temperature increased, there was more movement in the molecules and in result more distance. This will weaken the bond. After finishing all these steps, we will now see how this affects viscosity. Finally, in terms of viscosity, it is demonstrated that by increasing the temperature, the viscosity will decrease. This is mainly because in molecular terms, the Coulomb and van der Waals forces were weakened. The kinetic energy was increased and the potential energy decreased. This makes the movement of the molecules easier and in result the viscosity will decrease. The values show that the viscosity is inversely proportional to temperature. This is evidenced by the fact that the highest temperature has the lowest viscosity registered. In future studies, it will be interesting to observe the molecular dynamics of different fluids that occupy our quotidianity.
In conclusion, through molecular dynamics in GROMACS, it was possible to evaluate the effects of temperature on the viscosity of water. It was evidence that, at higher temperatures, the viscosity of water decreases. This is due to the fact that there is an increase in the kinetic energy of the system and a decrease in the potential energy, which translates into a greater movement of molecules and a decrease in the intermolecular forces of water. That way, the resistance of the water to flow decreases and the viscous forces are overcome by the kinetic energy.